Good day, my dear students. Welcome to the third part of our course, the anti-differentiation of a function. Then we have the following learning targets. Illustrate an antiderivative of a function and compute for the general antiderivative of a polynomial, radical, exponential, and trigonometric functions. For main discussion, let us first recall how to find the derivative of a function. Consider the problem. Find the derivative of f of x equals 3x to the fourth power. Applying differentiation rules, we would be able to get the derivative of the given function. We will have 12x cubed. In arithmetic, if we have 3 plus 4 equals 7, and we would like to find out whether we got the correct sum, we have to undo the process. Now, to undo the process, we are going to use the inverse operation of addition. So, in order to tell whether we have the correct answer or the correct sum, we have to subtract 7 minus 3. Our answer should be 4. With this, 7 minus 3 is really equal to 4. We can confidently say that 3 plus 4 is equal to 7. In finding whether we got the correct form of the derivative of the given function, we also have to undo the process, and that process is called the anti-differentiation. Anti-differentiation is the process of finding the function when its derivative is given. Let's have first how to read this expression. This expression is read as the antiderivative of 12x raised to the third power, wherein we have the integral sign and the integrand. Here are some rules that we can apply in getting the antiderivative of a function. The first set is about the basic integration formulas, while the second set are the integration formulas involving trigonometric functions. Now let me show you how to apply these formulas by giving you examples. Example number 1. Evaluate the expression, the antiderivative of negative 3 dx. Applying rule number 3, we will have negative 3x plus c. Can we use rule number 4 in getting the antiderivative of negative 3 dx? Let's see if we can have the same answer. Take note that the antiderivative of negative 3 dx can be written as the antiderivative of negative 3x raised to the 0 power dx. Applying rule number 4, we will have negative 3x raised to the 0 power plus 1 over 0 plus 1 plus c. Now simplifying this, we will have negative 3x plus c. Now we have arrived at the same answer, just as when we have applied rule number 3. Now let's have example number 2. Evaluate the expression, the antiderivative of negative 24x raised to the fifth power dx. Applying rule number 4, we will have negative 24x raised to 5 plus 1 over 5 plus 1 plus c. C here is the arbitrary constant. Remember that the derivative of a constant is 0. Now simplifying the expression, we will have negative 24 x raised to the 6th power over 6 plus c. We can cancel the GCF of 24 and 6, so we divide each number by 6. 24 divided by 6, we will have 4, and then 6 divided by 6 is 1. Simplifying further, we will have negative 4x raised to the 6th power plus c. Okay, now if you would like to check, you can find the derivative of the given function negative 4x raised to the 6th power plus that constant. So we'll just have negative 4x raised to the 6th power. Applying differentiation rules, we will have f prime of x equals 6 times negative 4 is 24. Then we deduct by 1 degree, so we will have 6 minus 1. So we will have negative 24x raised to the 5th power, which is the same as our problem. Now what about the antiderivative of negative 24x raised to the 5th power minus 10x dx? By applying rule number 8, we can have the antiderivative of negative 24x raised to the 5th power dx minus the antiderivative of 10x dx. Now getting the antiderivative of the first term, we will have negative 24x raised to 5 plus 1 over 5 plus 1, and then minus 10x raised to 1 plus 1, and then the arbitrary constant c. Simplifying this, we will have negative 24x raised to the 6th power minus 10 over 6 minus 10x squared over 2 plus the arbitrary constant c. So we can extract the GCF, which is 6. We will have negative 4, then we have 1. Okay, then here we have 5, we have 1. So simplifying further, we will have negative 4x raised to the 6th power minus 5x squared plus c. Therefore, the function having a derivative of negative 24x raised to the 5th power minus 10x is that function defined by negative 4x raised to the 6th power minus 5x squared plus c. Now let's evaluate the antiderivative of 4x raised to negative 5 dx. Now doing the same thing, we will have 4x raised to negative 5 plus 1 over negative 5 plus 1 plus c. Then we will have 4x raised to negative 4 over negative 4 plus c. We can cancel this, so we will have negative 1. This is positive 1. Therefore, we will have negative x raised to negative 4 plus c. Or we can have negative 1 over x raised to the 4th power plus c. Let's have example number 5. Evaluate the antiderivative of negative 4 over x cubed minus 8 over x to the 5th power dx. Now rewriting the expression such that there will be no term in the denominator, we will have negative of 4x raised to negative 3 minus 8x raised to negative 5 dx. Now applying rule number 8, we will have the antiderivative of negative 4x raised to negative 3 dx minus the antiderivative of 8x raised to negative 5 dx. Now applying rule number 4, we will have negative 4x raised to negative 3 plus 1 over negative 3 plus 1 minus 8x raised to negative 5 plus 1 over negative 5 plus 1 plus the arbitrary constant c. Simplifying, we will have negative 4x raised to negative 2 over negative 2 minus 8x raised to negative 4 over negative 4 plus c. Now simplifying each term, we will have negative 4 divided by negative 2, we will have 2x raised to negative 2. Now 8 divided by negative 4 is negative 2 times the negative sign, so we will have positive 2x raised to negative 4 plus c. So simplifying, we will have 2 over x squared plus 2 over x raised to 4 plus c. So the antiderivative of the given function is 2 over x squared plus 2 over x to the 4th power plus c. Okay, this time let's have example number 6. We are asked to get the antiderivative of the expression 15 over x raised to the 4th power plus 8 over x raised to the 5th power dx. Now, just like what we did in example number 5, we rewrite the problem. So we will have 15x raised to negative 4 plus 8x raised to negative 5 dx. Then apply rule number 7. We will have the antiderivative of 15x raised to negative 4 dx plus the antiderivative of 8x raised to negative 5 dx. And then for applying rule number 4, we will have 15x raised to negative 4 plus 1 over negative 4 plus 1 plus 8x raised to negative 5 plus 1 over negative 5 plus 1 plus the arbitrary constant c. So simplifying, we will have 15x raised to negative c over negative c plus 8x raised to negative 4 over negative 4 plus c. Now we divide the numerator and the denominator by negative 3. We will have negative 5x raised to negative 3. And then the second term, we shall divide the denominator and the numerator by negative 4. So we will have negative 2x raised to negative 4 plus c. Now we're writing the expression so that there will be no negative exponent. We will have negative 5 over x cubed minus 2 over x to the 4th power plus the arbitrary constant c. Now let's have example number 7. Evaluate the antiderivative of negative 14x raised to 5 halves over 2. Now we simplify first the numerical coefficient, okay, by dividing both numbers by 2. We will have 7, and here we have 1. So simply we will have the antiderivative of negative 7x raised to 5 halves. Now applying rule number 4, we shall have negative 7x raised to 5 halves plus 1 over 5 halves plus 1 plus c. Simplifying the exponent, we shall have 5 halves plus 2 over 2, and then in the denominator we also have 5 halves plus 2 over 2, and then the arbitrary constant c. So in the numerator we will have 7 halves. In the denominator we also have 7 halves. Simplifying further, we will have 2 multiply and then get the reciprocal of the divisor. So then we can cancel 7. So this is 1 and this is also 1. So what remains is negative 2x raised to 7 halves plus c. Now we're expressing negative 2x raised to 7 halves in radical form. We will have negative 2x raised to 3 and 1/2. So therefore we will have negative 2x cubed square root of x plus c. Let's have example number 8. You're asked to evaluate the antiderivative of 5 times the cube root of x squared over 3. Now we just rewrite the radical expression into an exponential expression, so we will have 2/3. Okay, then applying rule number 4, we shall have negative 5x raised to 2/3 plus 1 over 3 all over 2/3 plus 1 plus the arbitrary constant c. And then we will have negative 5x raised to 2/3 plus 3 over 3 all over 2/3 plus 3 over 3 plus c. Now we will simplify the exponent. We will have 5/3 over 3, and then in denominator we will have 5 over 3, okay, plus c. And then simplifying the complex fraction, we shall have the inverse operation, and then the reciprocal of the denominator. So we can cancel 3 and 3, then 5 and negative 5, so we'll have negative 1. Okay, so the result would be negative x raised to 5/3 plus c. Now rewriting this in radical expression, we will have negative x times the cube root of x squared plus c. Okay, that's example number 8. Now let's have example number 9. Evaluate the antiderivative of x raised to negative 1 dx. Now as you can see, if we will apply for rule number 4, we will have an exponent of 0 after simplifying the expression. So take note that in rule number 4, it is also given that n should not be equal to negative 1. So that explains that rule number 4 will not be used in evaluating the given expression. But instead, we shall use rule number 5. This expression can be rewritten into this form. X raised to negative 1 can be 1 over x. Okay, so that we can clearly see that it's really rule number 5 that we are going to use. So we will have ln of the absolute value of x plus c. So that's the antiderivative of x raised to negative 1 dx. Now let's have example number 10, wherein we still have x raised to negative 1. So we rewrite this. So we will have the antiderivative of 3 times 1 over x dx. Now we can have 3 times the antiderivative of 1 over x dx. Applying rule number 5, we will have 3 times ln of the absolute value of x plus c. That's it for example number 10. Now let's try example number 11. We are given the antiderivative of negative e raised to the x power dx. Now we can apply rule number 10. So the antiderivative of this expression would be 1 over a times e raised to ax. Now this expression can be simplified using rule number 10, wherein we have to determine the value of a. In this case, we have a equals 1. So you shall have negative 1 over 1 e raised to x plus c. So therefore, we'll just have negative e raised to x plus c. Now let's have example number 12. This time we have the antiderivative of 2e raised to 3x. Here a is equal to 3. So we will have 2 times the antiderivative of e raised to 3x dx. Applying rule number 10, we can see that a is equal to 3, so we shall have 2 times 1/3 e raised to 3x plus c. So simplifying this, we shall have 2/3 e raised to 3x plus c. Let's have example number 13. Now to evaluate this expression, we shall use rule number 9, wherein we can identify that a is equal to 5 and n is equal to 1. Now, rewriting this, we can have 3 times the antiderivative of 5 raised to x dx. Then apply the rule number 9. we will have 3 times 1 over 1 times 5 raised to x over ln 5 plus the arbitrary constant c. So simplifying this, we shall have 3 times 5 raised to x all over ln 5 plus c. Now let's have example number 13. Since in this expression we have the Euler number, we shall use rule number 10, where A is 4. Okay. So let's apply rule number 10. So we shall have 1 over 4 e raised to 4x plus c. Now what about if we have the antiderivative of a trigonometric function? So at the right, you can see here the different formulas that we can use in evaluating the antiderivative of a trigonometric function. Now in example number 15, we can see that the trigonometric function involved is sine x dx. So we shall use rule number 2. Now take note that we can write this as negative 5 times the antiderivative of sine x dx. Applying rule number 2, we will have negative 5 times negative cosine x plus c. So negative times negative, we shall have positive, so cosine x plus c. Now let's have example number 16. Now we have here this expression. Now looking at the rules, okay, we shall use rule number 4. Okay, let's rewrite first by writing negative 3 before the integral sign. So we can see clearly that we're just going to evaluate the antiderivative of cosecant x times cotangent x dx. Now applying rule number 4, we will have negative 3 times negative cosecant x plus c. Simplifying this, we will have 3 cosecant x plus the arbitrary constant c. Number 17, we are asked to evaluate the antiderivative of 2 over secant x dx. As you can see in the list of rules, we cannot use any rule directly in order to evaluate this expression. However, we can rewrite this as 2 times the antiderivative of 1 over secant x dx. Now remember that 1 over secant x is just the same as cosine x. Okay, this is one of the trigonometric identities that we have studied previously. So rewriting the expression, we will have 2 times cosine, 2 times the antiderivative of cosine x dx. This time we can use rule number 1 in evaluating the given expression. So we shall have 2 times sine x plus c. That's example number 17. Now let's have example number 18. Example number 18. Evaluate the antiderivative of cotangent squared x plus 2 times tangent squared x minus 5 dx. Now in the set of rules, we cannot find any rule which we can directly apply in order to evaluate this expression. However, just like what we did in the previous examples, we're going to make use of the trigonometric identities. So let's draw the super hexagon in order to recall the different trigonometric identities. Okay, so opposite we have cotangent, and then we have cosecant, and then we have secant. We have one in the middle. Now, as you can see, there is an exponent 2 above the trigonometric function. So with this, let's use the different Pythagorean identities. So for cotangent squared, we shall have, okay, we can use 1 plus cotangent squared x equal to cosecant squared x. Now, therefore, cotangent squared x is equal to cosecant squared x minus 1. So, replacing cotangent squared, we shall have cosecant squared x minus 1. Now, for tangent squared, let's form first the Pythagorean identities that we are going to use. So you shall have tangent squared x plus 1 equals secant squared x. So tangent squared of x is equal to secant squared x minus 1. So replacing tangent squared x, we will have secant squared x minus 1. And then minus 5, okay, gx. Now, getting the antiderivative of each term, we shall have the antiderivative of cosecant squared x dx minus the antiderivative of 1 dx plus 2 times the antiderivative of secant squared x dx minus 2 times the antiderivative of 1 dx, and then minus the antiderivative of 5 dx. Now simplifying, the antiderivative of cosecant squared x is negative cotangent x. Now the antiderivative of 1 is x. Then we shall have 2 times the antiderivative of secant squared x is tangent x. And then we shall have negative 2x. Now for the antiderivative of 5 dx, we shall have negative 5x plus the arbitrary constant c. So then, combining similar terms, we shall have cotangent x plus 2 times tangent x. Okay, combining negative x, negative 2x, negative 5x, we shall have negative 8x plus c. So therefore, the antiderivative of the given function is negative cotangent x plus 2 times tangent x minus 8x plus c. Now let's have example number 19. This time, again, we cannot find any rule which we can directly apply in order to evaluate this given expression. So let's rewrite first in order to see clearly what rule are we going to apply. So what if we write 3 tangent x over cosine x minus 2 cosine squared x over cosine x. Okay, then we have dx. Now applying trigonometric identities, we can simplify this term. The first term can be written as 3 tangent x. Now applying reciprocal identity for 1 over cosine, we will have secant x. Okay, why do we have that? 1 over cosine x is equal to secant x. Okay, now canceling cosine, we will have 2 cosine x dx. Now rewriting the first term, we can have 3 times the antiderivative of secant x tangent x dx minus 2 times the antiderivative of cosine x dx. Now, we can now use rule number 5. So we will have 3 secant x, and then for the second term, we can use rule number 1. So we shall have 2 times sine x plus the arbitrary constant c. Hence, the antiderivative of the given expression is 3 secant x minus 2 sine x plus c. Okay, thus, the general solution to the given expression is 3 secant x minus 2 sine x plus c. Now let's have the last example. Let's determine the function having the derivative of cosine x over sine squared x dx. Now, we can rewrite this as cosine x over sine x times 1 over sine x dx. Now, using quotient identity, note that cosine x over sine x is equal to cotangent x. So simply we can write this as cotangent x. And then 1 over sine x is equal to cosecant x. Okay, using the reciprocal identity. So 1 over sine x is cosecant x. So the problem given to us is equivalent to the antiderivative of cotangent x cosecant x dx. Now we can use rule number 4. So we can just write this simply as negative cosecant x plus c. I hope you were able to get that. And let's see if you were able to achieve the learning targets that we have set a while ago. Can you now illustrate an antiderivative of a function? Now, can you now compute for the general antiderivative of a polynomial, radical, exponential, and trigonometric functions? If not yet, you can send me your queries through the comment section. Thank you for being with me today.